Thanks for the introduction. It's a pleasure to be here, and I'd like to welcome you to my talk. I want to present some early results regarding an unexpected observation during my main work, focusing on very high cycle fatigue regime regarding the influence of the vibration behavior and the resulting fracture surfaces of two high-strength steels. I'd first like to start with a brief introduction regarding the used test setup, as well as the specimen geometry and obviously the tested materials. Then I'd like to show a basic comparison of this observation of the differing resulting fracture surfaces, then followed by a roughness measurement of those surfaces using confocal microscopy, and showing the differences in surface morphology. I'd like to conclude with an actual comparison of a natural frequency and ultrasonic amplitude data during the fatigue test. So schematically shown here is the in-house built ultrasonic test setup consisting of a piezoelectric converter, 3 boosters, and the specimen shown on the right. All the parts, including the specimen, are designed in such a way that the displayed longitudinal standing wave is formed, with the maximum stress being found in the center of the specimen. All the tests were performed with a load ratio of R-1, with a nominal testing frequency of 20 kilohertz. The ultimate number of cycles were 10 to the power of 9. And to avoid a significant self-heating of the specimen, the pulse pause mode, the tests were performed in a pulse pause mode, and additional soft air cooling was used. The tested materials were both quenched and tempered high-strength steels, 52-100 and 40-140, with a martensitic state, resulting in the given hardnesses. And the main difference is the significantly lower fatigue fracture toughness of a 52-100 when compared to a 40-140 steel. Displayed here is the fracture surface of a 52-100 specimen, failing at an internal non-metallic inclusion, and a smooth fracture surface area around the so-called fisheye is observed. Outside of this fisheye, we see, as expected, a forced fracture with a crack ridge height increase over the crack propagation. So to put it bluntly, this surface is pretty much straightforward. However, in case of a 40-140 steel, while still observing crack initiation at the non-metallic inclusion in the inside of a specimen, and still the formation of a fisheye, contradictory to the 50-100 and very unexpected, we observe several beach marks as well as a heterogeneous fracture surface area, which is hardly observable. We have an alternation between a brighter, a darker, a brighter, and a darker area in the bottom of this picture. To actually make those differences more tangible and quantifiable, we performed the roughness measurement along the crack path in 7 profiles, with the average roughness being displayed on the right with the dotted lines. Overall, as expected, we see an increase in average roughness with distant to crack initiation and a relatively large scatter. To reduce the scatter and actually get more robust values for the average roughness, we also did a circular roughness measurements, and the results are displayed here. Like I said, as we expect, we increasing roughness with increasing distance to crack initiation, and we were able to reduce this the scatter. We did the same. We performed the same procedure for the 40-140 steel, with the results being displayed in blue. While still observing an increasing trend, most strikingly, in the darker areas close to the final fracture, we observe significantly lower roughness measurements in both measurement directions, comparable to the roughness inside the fisheye. To now get to the actual reasoning behind why we observe such roughness deviations between the two specimens, we observe the surface fracture morphology. Starting again with 50-100, we have a grid of SEM images on the left with their respective positions being marked on the right. So inside the fisheye, we observe a rather smooth fatigue fracture surface, while outside the fisheye, we observe a ductile forced fracture with dimples or honeycomb-like structures. Overall, increase in surface topography roughness is observed, resulting in the increasing roughness shown before. However, in case of a 40-140 specimen, while still observing a rather smooth fatigue fracture surface inside the fisheye, and also the beach mark in the brighter areas, for example, see image E, we observe an intergranular forced fracture. Most strikingly, we see an alternation between an intergranular forced fracture in the bright areas, followed by a fatigue fracture with a relatively smooth surface area. And we see an alternation between those different fracture surface morphologies. Just simply based on the linear elastic fracture mechanics model, we would actually expect an increase in stress intensity factor, and therefore not this alternation between force and fatigue fracture. Shown here is an excerpt of actual generator data during the failure. Again, starting with 50-100 specimen. Displayed is the power as well as the frequency and the amplitude. The pause times between the post-pause modes were cut out. So each of those blocks corresponds to one impulse with roughly an average of 5,000 cycles. We also observe a similar pattern for the power, as well as a nearly constant frequency, as well as maximum amplitude during the whole test. However, if we zoom in close to the failure and actually have a look at the natural frequency as well as the amplitude, we observe a sharp drop in natural frequency as well as amplitude. If we calculate the area of the fisheye, or if we measure the area of the fisheye and then calculate the maximum stress intensity factor using Murakami's law, as stated or seen in the presentation before, we see that the actual value of the maximum stress intensity factor at the border of the fisheye corresponds very well to the fracture toughness, therefore resulting in unstable crack propagation and resulting also in the continuous fracture surface seen above. However, if we do the same for the 40-140 specimen, while still observing nearly constant values throughout all of the tests, if we zoom in close to the final fracture, we see a much slower and more prolonged decrease in natural frequency as well as amplitude over several pulses. Again, while measuring the area of the fisheye now touching the surface, so we have to account for surface defects, and calculating the maximum stress intensity factor at the border of this fisheye, we see that the fracture toughness of the 40-140 material is not reached, therefore resulting in a much slower decrease of natural frequency as well as amplitude, actually influencing the formation of a fracture surface. So with an increase in defect size, we would increase the area of the fisheye. However, due to the drop in natural frequency, we also reduce the amplitude, and therefore we get this alternation between force and fatigue fracture. So as a conclusion, we can summarize following points. Depending on the material, either an abrupt or a slow and prolonged decrease of the natural frequency and amplitude are observed. Therefore, the unstable crack propagation and this defect size resulting in the amplitude decrease seem to compete with each other. And the critical defect size seems to exist where, at which the natural frequency as well as the amplitude drop significantly. If a fracture toughness is reached before this critical defect size is formed, no influence on the amplitude decrease on the late crack propagation can be observed. However, if the fracture toughness of a material is higher, and therefore the critical defect size is reached before unstable crack propagation is actually started, the crack propagation is significantly altered due to this amplitude drop. I'd like to thank the colleagues from Karlsruhe Institute of Technology for the manufacturing of the specimens, as well as the German Research Foundation for funding of the main project. And obviously, I'd like to thank you for your attention.